Let's get started. So it's my pleasure to introduce Ronan Collobert, who's a distinguished research scientist at Apple in machine learning research, where he leads the MLX efforts, pushing ML innovation on Apple Silicon. Previously, he was at Meta for 8 years and NEC Labs for 6 years, interleaved with a short academic career of 4 years at IDIAP Research Institute in Switzerland. Ronan's research interests are around deep learning in general, efficient algorithms in particular, with applications in natural language, image, and speech processing. He received several Test of Time awards for his early work on deep learning for NLP and speech processing. In addition, he's a fervent supporter of open source, and since the early 2000s, he has led a number of popular machine learning projects, including Torch, Flashlight, and more recently, MLX. So Ronan, thanks for being here, and take it away.
Thanks a lot. Thanks for the intro. Okay, so I'm Ronan. I'm a research scientist at Apple. And if you heard about the keynote talks this morning, Chris talked to us about how language model research evolved through the years. And Brian talked about GPUs, which are actually powering a lot of the research that is happening there. So my talk lies a bit in between. It's about the software, which lies between the hardware at hand and the research you are doing. And today, the software I'm going to talk about is MLX, yet another machine learning software, but a machine learning software tailored for Apple Silicon. So I've been in machine learning software for years, and starting with Torch in 2000, I could not find an earlier screenshot, but that gives you an idea. And Torch evolved, many versions, forked into PyTorch later. So why I have been doing that? Why pushing for machine learning software all my career? So one reason is because as a machine learning researcher, I strongly believe that the tool that you use actually shapes your research, right? So in that respect, the tool that you use is also very tied to the hardware at hand. So there has been always like this kind of co-evolution loop between the hardware at hand, the software which powers this hardware, and your machine learning research. And if you look at history, in the early 2000s, there were already a number of people using GPUs for their deep learning research, but it was rather anecdotal. And then in 2010, NVIDIA released CUDA 3.0, which became convenient enough that major frameworks like Cyrano or Torch started to integrate a CUDA backend to support those GPUs. And from there, basically, the deep learning research kind of exploded. So there were major advances right away in NLP and vision. And NVIDIA understood very quickly that, well, maybe it's a good idea to focus on GPUs which actually can just do compute. And that's what happened with the Kepler and Pascal architectures. Shortly after, we've seen more research going on exploiting those GPUs, more frameworks exploiting also those GPUs to power the research, like Caffe, Caffe2, or PyTorch. And the story continues. Later, Google released TPUs and the associated software, TensorFlow and later JAX, which both supported GPUs and TPUs. More research was popping up the transformers, which were critical for the community. And the hardware kept scaling as the research, the ML research kept scaling to the language models we have nowadays. And that continues. We see more and more specialized hardware for our research, and in return, our research becomes more and more specialized for that hardware. So one hardware that I kind of missed here is actually the Apple Neural Engine, which was released in 2017, and later in 2020, Apple Silicon, which was the first instance of the M1 lineup, which powers probably many of the laptops that you have today. So in that respect, this piece of hardware, didn't co-evolve with the previous machine learning software or all this research which happened before. And we thought that was like an opportunity to actually build a machine learning software, really tailoring that hardware. And that's what, the story of MLX. MLX is about supporting machine learning research on Apple Silicon. So when we designed MLX, we were kind of late in the game compared to other frameworks. So in that respect, we were also lucky because we could look at what was out there. There were already a bunch of popular machine learning software that many people are using, like for example PyTorch, TensorFlow, or JAX. And each of them come with an interesting feature which makes them popular somehow. So for example, PyTorch comes with eager execution. And eager execution makes it very easy to prototype and debug. And that's one of the reasons that PyTorch became super popular amongst researchers. TensorFlow, on the other hand, comes with graph-based execution. So that's a bit different, but that allows more optimizations. Later, they added a compiler, XLA, which also allowed even more optimizations. JAX also relies on this compiler, XLA. And JAX features a NumPy API, which is very interesting for people already familiar with numerical computing. And it's a powerful API. And in addition to that, they added composable transformations, which is a great idea. Also, improving the powerful API. So with MLX, we tried to blend all these nice features into a single framework. So MLX features a NumPy API. We borrowed the composable transformation idea from JAX. We have lazy execution, which is a bit between eager execution from PyTorch and graph-based execution for the earliest version of TensorFlow. And under the hood, we manipulate on the fly a dynamic graph, which can be, if you want, compiled. So we have a simple compiler which enables further optimizations if needed. The stack of MLX looks a bit like the stack of other machine learning frameworks. I would argue that we try to make it as simple as it gets, such that anyone with a decent programming background could understand it from A to Z. So we own the full stack from low-level kernels, like CPU kernels written in C, or GPU kernels written in Metal for Apple GPUs. And on top of that, we have a layer written in C++, the MLX core, which is fully fledged. You can actually use MLX in C++ if you want. On top of that, we have actually mirrored MLX in C as well, which makes it very easy to wrap in other languages. And we have higher level language support, like Python or Swift, which is important for Apple Silicon. And in addition, you have even higher level packages like MLX-NN for neural networks, and or language models packages built on top of that as well. So looks a bit similar than other frameworks, but I'm going to dive into the details and show you the key differences. But I will start with what looks actually most familiar for you. That is the core written in Python and the neural net package. So the core is actually providing a NumPy API. So if you are familiar with numerical computing and NumPy, you should really feel at home. We support arrays, any operation, most of the operations that NumPy supports. So it should not be very different than what you are used to. On top of that, we support composable transformations borrowed from JAX. So transformations are basically something which takes a function and is going to return another function. So it transforms a function into another function. And a popular one is, of course, for machine learning, is grad, which computes the gradient of a functions. So here, we, for example, show an example where we define a loss function, and we compute the gradient of this loss function. And given those transformations, operates on functions and return functions, they are actually completely, nestable, so you can nest them if you want to. On top of this core layer, we have a neural network package, and it's very similar to PyTorch in spirit. As in PyTorch, basically, you have like a top class, like the module class, and if you want to define a new neural network, you are going to inherit from this class. You are going to define the layers you want in this MLP, in the constructor, and you are going to compute the output of this MLP, sorry, in like the call function. And it may use, of course, the layers you've defined in the constructor. So very similar to PyTorch in spirit, there are only minor differences. So far it was maybe a bit boring because I didn't show the differences. So why another framework, you would say? And now I'm going to focus on what makes MLX really unique. And as I said, we are providing a framework which is really tailored for Apple Silicon. And Apple Silicon features unified memory. What does it mean? It means like the CPU, the GPU, and in fact, the neural engine can all access the same memory. So in that respect, we change a bit the programming model in MLX. It's slightly different than what you are used to, but this difference is actually quite important. Arrays live in unified memory, so there is no reason to actually tie them to a particular device. In contrast, operations are tied to a particular device. And in fact, you can schedule several operations, if you want to, on different devices using the same input arrays. And in this example, if you do that, those operations will actually run in parallel, one on the CPU and the other one on the GPU. Another cool thing with MLX is that the core API is actually full-fledged and available in multiple languages. So for example, here is an example on how you would write the transformer attention in Python. Sounds familiar, but you can do the exact same thing in Swift if you want. Or if you are very familiar with C++ and don't want to bother with higher level languages, you can do the same in C++, with almost the same number of lines of code, which is kind of amazing. We have actually, an API also in C. I didn't show it here because it's slightly more verbose because you have to handle allocations and deallocations. But the C API makes it super easy to wrap MLX into whatever language you like. And in fact, the community has written a number of higher level APIs in Rust, Node.js, Elixir, and so on. Another key ingredient of MLX, which is quite different than what people are used to in PyTorch and TensorFlow or JAX, is like a lazy evaluation. What does it mean? So in fact, in MLX, everything is lazy. If you do some allocation like here, allocating a very large array, nothing will happen. The framework is lazy. It's waiting for you to say, hey, I actually want this array. And the way you say that is by saying, eval this array. When you do that, then here it's going to explode because it's running out of memory. A print statement would also trigger an eval because under the hood, it actually says, I actually want to see this array. But everything in MLX is lazy, which means whatever computation you do, if you want the actual results, you have to specify it with eval. So lazy evaluation is kind of an overlooked feature, and maybe it's hard to see the implications. So let me try to give you a taste of some of the implications. So let's say you just bought a shiny new M3 Ultra, fully loaded with memory, and you want to run some of the largest language model out there on that, like DeepSeek R1. It's more than 600 billion parameters. It's in FP8. It's not going to fit in memory. So if you try to load this language model the standard way, let's say the eager way, the eager execution way, you will basically load a bit, few layers, and then it's going to explode, right, out of memory. If you try the lazy way, nothing will happen because you're not using the language model yet. So if you want to, for example, just inspect part of the language model, like, for example, the embeddings, then something will happen. Then only the embeddings will be instantiated because that's actually what you need. So that's what lazy evaluation allows. You can still use load model. It will kind of do everything as if it loaded the model, but nothing happens. And only if you need part of the models, it will actually instantiate what you need. On those type of machines, most likely you will want actually to run the model in a compressed manner. So you will quantize it somehow. And a popular quantization is like 4-bit quantization. And if you do that with a lazy approach, well, you will operate on the full precision weights. But given you are using the low precision weights, there are no reasons to have all the full precision weights at the same time in memory. Instead, it will be all the low precision weights. So that will allow you to run this language model seamlessly on your device. Another interesting feature of lazy evaluation is it actually simplifies your code in many places. It's a bit hard to see. So here I try to give an example where one computes a bunch of norms, three different norms. You don't know in advance, which norm the user is going to use. But in a lazy evaluation framework, it doesn't really matter because if, like here, the user is using only the L2 norm, well, only the path of computation related to the L2 norm will be actually evaluated. So you don't care about the rest. It doesn't matter if you wrote it, In an eager framework, this would be evaluated, but here, only the parts that are of interest are going to be evaluated, which is kind of convenient because you don't clutter your code with if conditions everywhere. All right. Another interesting feature of MLX is the way we manipulate the graph of computation. So when you define a function like, for example, here, RMS norm here, and you call this function, under the hood, we are going to, on the fly, build a computational graph. So if you call it over X vector, you are going to have under the hood such graph being built on the fly. And we do that very efficiently. And when you need the results of this computation, you are going to call an eval. And the cool thing here is that eval will see the graph of computation entirely. So it can actually do some optimizations if it wants to. And typical optimizations are, for example, buffer donation to save memory. Or it can be also parallel execution for nodes of the graph which don't depend on each other. So in that respect, lazy evaluation is quite powerful. But it means that the way you manipulate the graph needs to be on the fly and super fast, so with very low latency. So we try to push that quite hard with MLX. So latency of graph manipulation is a bit hard to benchmark, but actually there is a good old benchmark which exists out there, which can be used for these kind of things. It's MNIST. We would think that MNIST would be still used in 2025. But MNIST is for those who remember, it's a small data set with small digits. So all the operations that you do on them are small. And here we use this benchmark to train a classifier using a feed-forward neural network with a number of layers, which we varied on the x-axis. And we measure the iteration time on the y-axis. So the cool thing with this benchmark in 2025 is that you are basically bottlenecked by the graph manipulations, the overheads of your framework, rather than the compute. So it kind of allows you to analyze, okay, how are we bottlenecked with overheads or latency? And here you see that clearly PyTorch has much more overheads than MLX when it comes to graph manipulation. So one could say, hey, yeah, of course, but that's why we invented compiler, right? I can compile this whole graph that we are using many times, and in that respect, I will then have no latency issue anymore, manipulating this graph because it will be compiled. So it's true, and in MLX we also have a compiler, but one big difference with other frameworks is that given we pushed very far the low latency on the on-the-fly graph manipulation, we did not have to work too hard on the compilation side to be on par with other frameworks. So we do have a compile function, but it's rather, kind of a simple compiler. It does graph simplifications, it fuses all the element-wise operations, and it also fuses, a bunch of various no-op operations. So to give you an example, if you define a GELU function, it will correspond to this kind of graph here, which actually account for many nodes in a graph already for a simple function like that. But all these operations are actually element-wise, which means that a compile call will transform this graph into a single node graph, which will mean that there are much, much less overheads in terms of graph manipulations, because now I have only one node for that particular operation. So in addition, our compiler has a cool feature, which is it supports shapeless arrays, which means that you do not need to recompile each time you have a different shape, an input shape. So it does not work for all operations, but it works for many operations. So if you have a graph which uses operations which support this feature, you can actually compile it shapelessly, which is kind of powerful as well. Our compiler is also very fast. So here, it's a benchmark where on the x-axis, we compile a neural net with 10, 100, or let's go crazy, 1,000 layers. So from not many nodes basically to many nodes in the graph, and we compare the performance of the compilers of PyTorch and MLX. And as you can see, PyTorch can take up to several minutes to compile such simple graph, while MLX takes basically just a few seconds. So, no offense. I mean, of course, it would not be interesting if the compiler was not doing anything, right? So I had to show the result, okay, what do we gain when we compile? So let's take again, this MNIST example, same than before. Now let's compile, both frameworks. So with PyTorch, you gain huge performance. You get a huge boost in performance because you get rid of all these graph manipulations. In MLX, you actually also get some performance boost, a bit less. But the reason you get this performance boost is not really because of the graph manipulation, but rather than the fusion operations which are going on under the hood. All right, guess what? If you want to try MLX, it's actually open source. And it's available on GitHub. And we have a GitHub org, so you can go there, check out the repositories. There is the MLX repo, core repo itself, but there are examples. There are specific repositories for language models, and so on. When we released MLX less than 2 years ago, we were really amazed by the traction we got from the community. And the traction keeps going, right? So this work, would not have been possible without the community. We got also a lot of traction on Hugging Face with more than 3,000 members, and about the same in terms of models specific to MLX. And there is even MLX My Repo, which allows you to quantize any model with MLX directly on Hugging Face. So what people do with MLX? Seriously. So there are a lot of applications that we have seen, ranging from research papers to actual apps powered by machine learning or in general like language models. There are people, stacking Macs together and, for example, doing inference of very large language models in a pipeline manner. There are even people, fine-tuning their language model on their laptop while traveling, and people using it for physics, all sorts of applications. But the two main applications that struck us was were like large model inference and large model fine-tuning on a Mac. So those got really popular right at the beginning with MLX. So in that respect, we try to push them as state-of-the-art as possible with MLX. So I'm going to talk a bit on how we actually pushed, the state-of-the-art of running language models on Apple Silicon with MLX. One problem with large language models is that they are large. And because they are large, they don't fit necessarily on your computer. So, for example, if you take the largest, DeepSeek R1 or the largest quencoder, those, if you take them in native precision, they are not going to, fit on your computer. They are going, except if you have a massive computer that I don't know about, but they are going to take, more than a terabyte of RAM. And even if you bought your latest Mac Studio fully loaded, it's not going to fit in memory in native precision. So, of course, people compress those models. And a popular compression is quantization. Quantization in 4 bits is even more popular because it's a good trade-off between compressing the model and not losing too much end-user performance. And so if you compress those models using 4-bit precisions, then all fit on a Mac Studio. And that makes the Mac Studio really cool to run those large language models. But that also means that we needed to support quantization properly. So in that respect, quantization is a first-class citizen in MLX. We have a bunch of quantization operations. And here are a few which are the most important ones, like the quantize function itself, which takes a bunch of weights and returns the quantized weights, and it supports different schemes. But here, there are also scale and biases, which are in higher precision and attributed to groups of weights. We have quantized matmul, which will take quantized weights and unpack them on the fly and perform a matrix multiplication. And we have also, the dequantize operation, which will get back an approximation of the original weights. But the cool thing with MLX is that they are actually first-class citizens, so they are provided in the core of MLX, but also they support grad, so you can actually backward through the scale and biases, for example. So that makes it very convenient in MLX to explore quantized-aware training techniques, for example. And in that respect, as I said, if you quantize a model, like here, a Qwen3, GEMA3, or a large Qwen3 mixture of model, you will most likely, lose in terms of end-user performance. Here, up to 25% of the original MMLU performance of the BF16 model. But you can try very simple, quantize-aware techniques, like, for example, try to match the unquantized model using, for example, a Kullback-Leibler loss, backwarding through your quantized model only the scale and biases and updating those, and you will recover, very easily quite a bit of the original performance of the model. So MLX really allows you to, explore this kind of techniques very easily because those operations are first-class citizen. Okay, so we wanted to make it easy for people to run large language models on Apple Silicon, so we also made a dedicated package for language modeling, a package which supports language model inference, language model fine-tuning, and quantization of language models. It also supports, access to the zillions models which are available on Hugging Face, which makes it very easy to try your favorite language model. And we have a command line support for the lazy people, but it's very convenient to chat with your model very easily. And we have also a corresponding Python API if you want more flexibility or if you want to build your research on top of it, for example. So we have, we support a number of commands. One of them is, just chatting with the language model. And here is a little demo. We are at BayLearn. I hope the wireless is robust enough. You could try to pip install MLXLM and run on your laptop your favorite language model. So here on the left, we have like a Mistral 7B language model, which is 4-bit quantized. And on the right, we have a very large, quite large, let's say, for a laptop, Qwen mixture model, 30 billion parameters with like only 3 billion parameters active. And as you can see, both run completely fine on like M2, MacBook Air M2 with only 24 gigabytes of RAM. The Qwen 30 billion parameter model gives kind of a hard time to the machine because it needs like 20 gigabytes, I think, to run. And remember, it's unified memory. So this memory is actually shared with the system and the graphics. So it's kind of amazing that this model actually runs on like consumer hardware, a consumer hardware device like that. So large mixture models actually run very, very well on this type of hardware. So if you have a fully loaded M3 Ultra, for example, you can try to run the largest model out there on a single node. Like here, we benchmark DeepSeek R1 and the largest Qwen encoder as well as GPT-OSS on like a single M3 Ultra in terms of tokens generated per second. And as you can see, they are all significantly faster than average human reading speed. So that makes it completely usable on a single node and again, consumer level devices. If you are not too much into command line, if you don't know about Python, there are still end user applications like, for example, LM Studio, which are nowadays sometimes powered by MLX. And you can interact with your favorite language model with that type of applications in a very nicely friendly environment. Which brings me to MLX Swift. So Swift is the language of choice on Apple devices. It's really what you need to use if you want to do whatever apps on device, for example, on your iPhone. So in that respect, it was important for us to support the Swift language in MLX. And for that, we created MLX Swift. And the cool thing with MLX Swift is that it basically brings numerical computing to Swift because we have now a NumPy API available in Swift. On top of this NumPy API, we built a neural network package, which is very similar to the Python one. Except that it's written in Swift and uses the Swift core API of MLX. So that allows to experiment with machine learning on device. Here on the left, we train NNIST. Remember this funny benchmark? So we train NNIST on like an iPhone on the left, and we even test it. And on the right, we test like a Gemma 2 billion parameter model using MLX Swift on an iPhone. So many people ask us, okay, that's cool. You have like a machine learning framework working on Apple Silicon. What about other hardware? So that's a good question because, as we just saw, MLX allow you to develop and train at, let's say, small, medium scale on your Mac. You can develop on your laptop. It's very convenient. Experiment a bit your research ideas. On the other end of the spectrum, if you have a model which is like fully trained, you can run local inference of your favorite model on your laptop as well with MLX. But in between, what happens? How do you train at scale on like many servers? So that's a good question, and we didn't have a solution until this July, where now you can also do that with MLX. So I have to put a disclaimer here. It's like, still experimental. We do have a CUDA backend now to run MLX on NVIDIA GPUs. But it's work in progress. It's not fully fledged, but it actually works pretty fine. And here is actually a benchmark where we train a 600 million parameter Qwen model comparing MLX on NVIDIA GPUs with PyTorch. So on a A100 and a H100. And those are the uncompiled versions of PyTorch and MLX. And we benchmark in terms of tokens ingested per second, like processed per second. So MLX actually, again, there shines when it comes to graph manipulations. We really don't have much overheads. So the uncompiled version is actually significantly faster than the PyTorch version. You can compile both frameworks, in which case they end up in the same ballpark in terms of performance. For this particular benchmark, we have a slight edge, but in general, it's the same ballpark. And, but we do have the advantage of the fast compilation. So there, PyTorch suffers from very long compilation time, up to several minutes. You can basically go grab a coffee, while MLX takes only a few seconds again. We do support inference as well. On your A100 GPUs, for example, here we run inference of 7B Mistral model in PyTorch. And PyTorch, you get like a real, a great boost in performance with PyTorch when you compile PyTorch, because there again, you need to manipulate the graph on the fly. So it's particularly intense for inference. Latency is very critical there. So you get a great boost in performance when you use the compiled version of PyTorch, the compiled version of the graph in PyTorch. For MLX, even the uncompiled version almost matches the compiled version of PyTorch, which is really an achievement by itself. And of course, given we don't need to compile there, we do not suffer those long compilation time. All right, so that's MLX, machine learning software for Apple Silicon, and also apparently works on NVIDIA GPUs now. So the co-evolution loop, between hardware, software, and machine learning research, started on that hardware with like the Apple Silicon hardware released in 2020. Yesterday, Apple actually released the M5 supporting like the GPU neural accelerator. So we have more work to do. So we got great hardware. We got like the software supporting machine learning on that hardware. Now we are basically waiting for your machine learning research, such that we can close the loop, the co-evolution loop. So if you're interested, check out our website. And I have to thank the MLX team, which is small, but really great, as well as the machine learning community, because all this work would not be possible without a community. Thank you.
Great. I think we have time for a couple questions.
Hi, thank you so much. Given that you knew that you were going to compile on Apple Silicon, what kind of optimizations were you able to make?
Yeah, so I mentioned those before. So we have graph simplification, which is going to, for example, remove like redundant nodes in the graph or nodes which are not used. We have element-wise fusion of all operations, and we have also, some fusion of like a bunch of other operations, but it's more anecdotal. So that's the most important ones.
Right.
Yeah.
Thank you. Yeah.
Of course, also, as for on-the-fly graph evaluation, we have also things like buffer donation and things like that for memory optimization.
Any other questions? Maybe I'll ask a question. Can you talk a little bit about the types of open source contributions that you're hoping that people make having open source the system?
Sorry?
Oh, can you talk a little bit about the types of open source contributions that you're hoping people make now that MLX is open source?
Yeah, so as I said at the beginning, machine learning research is always tied with the hardware at hand, right? So I think it's important to understand that with each new hardware, there is a possibility of new ML algorithms. And here we have like a piece of hardware which like supports a lot of memory, which is unified. So I do hope, that people will come up with ideas, for example, using both the GPU and the CPU at the same time. So that would be, the kind of things I'm looking for.
Great.
Thank you for your presentation. I have a quick question about the quantization that you do over here. Over here. So for your quantization, you said that the MLX framework supports FP4 precision. So, but I know like natively the M1 chip, like that series of chip doesn't support FP4. So how did you guys get that to work like with the chip?
Yeah. So indeed, currently the chips don't support, the hardware doesn't support lower precisions. So we do that on the fly. So basically, you unpack the weights on the fly, and you perform the actual computation in full precision. But it's going to be on the fly, so you are not going to use more memory, basically.
Okay, so like you pack the FP4 into a bigger.
Yeah, you unpack them, right? You unpack them on the fly.
Okay, thank you.
Yeah, one more question. Is there any plans on integrating MLX under XLA so that like there is a unification of?
I've heard this one before. I will add it, a check mark in front of XLA. So for now, we don't have any plans, but the more people ask, the more we'll think about it.
So Ronan, I have a key question. You're supporting many languages with your API. Do you support plain English?
I must admit that one of these slides, I will not say which one, was actually AI generated. I was surprised that AI could come up with MLX code already after 2 years of existence. So yeah, you can somehow. Yeah.
Great. If there are no other questions, let's thank our speaker.
Thank you.